Hello everyone, welcome to my talk. My name is Weihao. I'm currently a postdoc at the University of Washington. I'm going to talk about our work on meta-learning for mixed linear regression. This is joint work with my amazing collaborators Raghav, Zhao, Sham, and Sewoong. Our research is motivated by the following observation. In many modern machine learning settings, we have a large amount of data contributed by a large number of heterogeneous individuals, with each individual providing a modest amount of data. For example, Apple has hundreds of millions of phone users, and say we want to build an input method which can predict the next word the user is going to type in a text message. Each user has a different language model and only contribute to a small amount of text message data. Apparently, for each user, using that user's data alone is not enough to build a reliable language model, and we have to use the population information. In this setting, there are two related goals. First, we want to learn the population of models of parameters. Second, we want to use the knowledge of the population as a prior to improve the estimate of each user's model or new user's model. For both of our goals, the fundamental question here is, to what extent can a large number of data sources compensate for the lack of data of each source? Meta-learning tries to address this goal. In a meta-learning setting, there are n users. Each user has its own dataset of different sizes. For example, user 1 provides T1 number of examples, and there is a meta-training algorithm that takes all the user data and outputs a meta-parameter estimate theta hat. Now a new user comes with a dataset as mu y new of size tau, which is drawn from a distribution d nu. There's a training algorithm that takes the user dataset and the meta-parameter theta hat and produce a predictor phi hat. And the goal of the training algorithm is to minimize the expected loss of phi hat under d nu. Without any assumption, the new user might be unrelated with the previous n users, so how can we gain anything through meta-training? Well, we assume all the users are drawn from the same distribution, so the information about the distribution can be very helpful. For example, if we realize that all the n users are basically the same, then it's not unreasonable to guess that the new user will be the same as all the previous users, and the prediction problem becomes super easy. Having introduced meta-learning, let me talk about the model assumption of this work. In this paper, we assume there are k unknown regression vectors, W1 up to Wk. Each vector has dimension d. For given user I, let's assume for simplicity its regression vector beta I is drawn uniformly and random from the set of W's. Given beta I, user I has a dataset of size Ti, and each data point xij is drawn from a distribution P of x, and label Yij is beta I transpose xij plus independent noise. Like we have said, there are two related goals in this problem. The first is to learn the distribution of the regression vectors. In this case, it's completely defined by the set of W's. The second, we want to use the knowledge of the distribution to improve the estimate of a new user's model. So what is known about this problem? This is the CDF plot of the distribution of the user sample size for a meta-learning dataset. In this plot, x-axis is the number of examples a user has, and the y-axis is the number of users that has at least certain amount of examples. The blue shade depicts a realistic meta-learning dataset. For example, the x-axis starts from 1, and this point indicates that there are n users with at least one example. There are fewer users with a larger number of examples, and this point indicates that the largest sample size is Tmax. Classical mixed linear regression considers the case where each user has exactly one example. In this case, the best algorithm requires exponentially large number of users. In another extreme, when each user has ordered d examples, we can solve each user's regression problem independently, and we only need order k users to recover the k unknown regression vectors. However, the real data depicted in blue shade usually does not intersect with either of the 2 points. In this case, what's the best we can do? Well, ideally, we want as long as we have enough data points in total, in this case, k times c, even when t is very small, we can still recover the k unknown regression vectors. The green region covers the case where we have at least k examples in total. So ideally, we want to be able to learn when the blue shade touches the green region. Unfortunately, it is not previously known whether this is possible. Our results bring us one step closer to this goal. Our meta-learning algorithm requires two kinds of datasets as shown in the plot. The first kind is provided by the light users, where each user provides at least log k examples. The total number of examples provided by light users should be at least dk squared. The second kind of datasets are provided by the heavy users, where each user provides at least square root k examples, and they provide k-squared examples in total. These two requirements are shown as the light region and heavy region in the plot, and as long as the CDF of the dataset intersects both areas, our algorithm can be applied to the dataset. The log k requirement on the light user is relatively weak, so our algorithm roughly achieves the best we can hope for, except that we need a set of heavy users with square root k examples each. Once we have learned the meta parameter, learning is easy, and we show that a new user only needs to provide log k examples. For comparison, without meta-learning step, the new user needs to provide order d examples for learning to be possible. Our algorithm has three parts: subspace estimation, clustering, and classification. In the subspace estimation part, we compute the subspace spanned by the regression vector W with all users' data. This step requires each user having at least two examples, and we need dk squared examples in total. Once we learn the subspace, we can project the heavy use data onto the learned k-dimensional subspace, and now we have a k-dimensional regression problem. Since we assume k is much less than d, this step greatly reduces the dimensionality. In the clustering step, we k-cluster the heavy user dataset based on their pairwise distance. Then each cluster provides a rough estimate of one of the regression vector. This approach is inspired by the classical work of Vampala and Wang on mixture of Gaussian. This step requires each heavy user provide at least root k examples, and in total we need k-squared examples since now there are k different k-dimensional regression vectors. Finally, in the classification step, we grow the cluster by classifying each light user into one of the k clusters. As the cluster grows, we have more and more refined estimate of the regression vectors. This step requires each light user to have at least log k examples, and in total, they need to be dk over epsilon squared examples if we want epsilon error of our estimate. How do we estimate the subspace? For illustration, let's assume the distribution of X is isotropic. Recall that beta I is picked uniformly at random from the set of W's. So let's define Zi to be the index of W such that Wzi is equal to beta I. Our first observation is that given Zi, the expectation of Y times X is beta I. Given that, our second observation is that if we pick two different examples from user I, say xi1, yi1, xi2, yi2, and compute their outer product, we get an unbiased estimator of the second moment matrix of beta I. Since each user and each pair of examples give us an unbiased estimator of the second moment matrix, we can construct many such unbiased estimators and simply take the average of them, which give us a good estimate of the second moment matrix. And notice that the column space of the second moment matrix is precisely the subspace spanned by the set of W's, so we're done. This step requires t greater than 2, and since we need to be able to pick two different examples from each user. And in total, we need dk squared examples. After learning the subspace, we can project the data onto learned k-dimensional subspace, and problem becomes a k-dimensional regression problem. If a user has ordered k examples, we can solve its regression problem on its own. But what if the user provides much less than k examples? We borrow a very recent result by Kong, Valiant, and Brownscale in 2020. They show that given two k-dimensional regression problem, it's possible to estimate the correlation between the regression coefficients with only square root k examples each. If we apply this result for two users each with more than square root k examples, we can determine whether the two users share the same regression vector or not. We can k-cluster the users based on this information. If every cluster has order k examples, we can roughly estimate a regression vector for each cluster, and this requires k-square examples in total. The idea of a classification is to add more data points to each cluster to refine the estimation. The reason we separate clustering and classification is that once we have a rough estimate of W's, we no longer need square root k examples, and we only need log k examples to determine which of the W is beta I. Our algorithm looks at the variance of the residual for k different regression vectors. Notice that the variance of the residual is equal to the variance of the noise plus the squared L2 distance between beta I and the regression vectors WL. So the variance is small when L is equal to Zi. It turns out with a simple union bound argument, we only need t equal to log k to make sure WZI has the smallest residual variance among all the WLs. And this step requires each user to provide log k examples, and we need dk over epsilon squared data points in total if we want epsilon error. To conclude, in this work, we propose an algorithm that can efficiently utilize the light users' data as long as there are some heavy users, each with square root k examples. A natural question to ask is whether the heavy user is necessary. Also, what can we do when the heavy user has much less than square root k examples? Another interesting question is that our meta-learning algorithm focuses on parameter recovery, and certain separation assumption is necessary for parameter recovery to be possible. If we only care about predicting well on the new user, maybe we don't really need to recover the parameters. Our work assumes all the users have the same distribution over X. So what can we do when P of X is different across the different users? Finally, it would be interesting to consider this problem beyond the regression setting, maybe starting from binary classification. Thank you for your attention. Please refer to our paper for more details.